del curso de pruebas asistidas por computadora. Una vez más vamos a escuchar a Jay Mireles James. Gracias. Quería anunciar que las diapositivas y documentos y también las pruebas por computadora que nos enseñó John Philippe ayer están todas en la página del curso. La página del curso la tienen aquí. Entonces, por favor, ahí pueden ir y revisar las notas y ver las diapositivas que estamos
haciendo. Hay un error que no entra tal cual.
¿No entra tal cual? Bueno, eso lo puedo... no, creo que está bien, me acabo de revisar. Bueno, ok. Pero después lo podemos revisar. Creo que está bien la dirección y entonces ahí vamos a ir poniendo todo el material del curso. Entonces, vamos a empezar con Jason Mireles James en la primera sesión. En la segunda sesión tenemos nuevamente a John Philippe Desarrollo.
Okay. All right, thanks. So, yesterday I had the pleasure of giving a kind of introductory, kind of general talk about some ideas involving using the computer to prove theorems. Today, I'll try to get into more specific, kind of hopefully non-trivial applications of some of those ideas. So I want to recall two theorems that I had on the slides yesterday to start things off. Okay, so the first is a theorem involving what people call a blue sky catastrophe. It's just suppose you have a Hamiltonian vector field on R4. This vector field has a saddle focus equilibrium. And so 2D stable, 2D unstable manifolds. Those manifolds intersect transversely in the energy section. So you have a homoclinic orbit, right? If this is transverse, then the conclusion of the theorem is that there's a tube of periodic orbits that accumulate to that homoclinic orbit, right? So the existence of a single homoclinic orbit implies the existence of an uncountable family of periodic orbits with longer and longer and longer period tending to infinity. With the same hypotheses, the existence of a homoclinic orbit in this context implies the existence in the energy level of chaotic dynamics of a horseshoe. Okay? So, given a Hamiltonian vector field with a saddle focus equilibrium, if you could prove the existence of a transverse homoclinic orbit, then you would then know that you had these periodic orbits accumulating to the homoclinic orbit and that there was chaos nearby. Okay? It can be hard in applications to verify these hypotheses. So it would be nice to have machinery to do computer-assisted proofs that feed into theorems like this. And that's part of one of the things that I like about this kind of computer-assisted proof. You can use the computer to verify the hypotheses of theorems, which then give you a lot more rich dynamics. Okay, so here's a theorem that comes from the PhD thesis of Shane Kepley. So he proved as part of his thesis that if you take the restricted four-body problem with precisely these mass parameters, so 0.5, 0.3, and 0.2, then there is a transverse homoclinic orbit in this problem. Okay? So once Shane has proved this, then the theorems of Hernard and Dervany kick in, and as corollaries, you have the blue sky catastrophe, and you have the chaos nearby. Okay? So I want to try to actually talk about how you would prove something like this using the computer. And that's what I'll talk about today and tomorrow. Okay? Okay, so you need to do a number of things. First, you're given this vector field. You need to prove it has a saddle focus equilibrium. And this was the example that I did at the end of the lecture yesterday. So I showed how you could do this with computer-assisted methods. Then you need to do some validated computation of the stable and unstable manifolds. And once you've computed the stable and unstable manifolds, you need to show that they intersect transversely. So all of these things you have to do them with computer assistance. Okay? Well, before you could hope to validate any of those objects, you need to compute them. Okay, so the first step is to compute these things. And this isn't necessarily, it's not always easy. But you don't just want to compute the equilibrium, the stable, the unstable manifolds, the transverse intersections. You want to compute them in such a way that the computations can be validated. Okay, so the fact that you want to do a proof later informs maybe how you do the computations up front. So today, my talk will focus mostly on this, just how you compute things, right? But computing in a way that you'll be able to validate. And then tomorrow I'll come back to the validation, okay, to the computer-assisted proof. Okay, so just some notation I'm going to use a lot today. I'm going to be doing a lot of power series kind of computations. John Philippe went through some of this yesterday, so I'll go kind of fast because it's standard, but I just want to introduce my notation. So if you have two power series, you multiply them together, you get a new power series. The coefficients of that product is given by the Cauchy product, right? So like John Philippe talked about yesterday, if you have two infinite sequences, you can just define a product of those two infinite sequences, which is given by the Cauchy product. And I'll use this notation, okay, a lot. And it just means this. So another way to rewrite that product, the product of f and g, is it's just the sum of these coefficients of the Cauchy product. Right? And higher products are similar. So you need to cube something to the fourth power, to the fifth power, similar products, right? In more variables, it's exactly the same kind of thing, right? So if you, so I'll do some work today with power series of two variables. Okay, so if I have f and g, power series in x and y, you multiply them, then the power series for the product is given by, it has these Cauchy product, these Taylor coefficients given by the Cauchy product, for two variables. And, if you cube something or to the fourth power and so on, you have these formulas. So these are just loops you write in your computer if you're implementing something like this, right? You just have to sum all these things up. Okay. And if you had 3 variables, 4 variables, 10 variables, all of this generalizes, right? Okay. So the first problem I want to talk about now is what people refer to as a Taylor integrator. So what's the Taylor integrator? So I have a vector field, let's say real analytic, and an initial condition. So there's a real analytic solution curve satisfying the differential equation. It has a power series expansion. The 0th coefficient of the power series is the initial condition. I'd like to know the rest of the Taylor coefficients. So a Taylor integrator is just an algorithm which, given an initial condition and an order k to which you'd like to compute, this algorithm should return these coefficients to you, okay, to whatever order you wish. So here's a simple, kind of the simplest nonlinear differential equation I could think of. I look for a power series solution, right? I mean, this is almost verbatim what John Philippe was doing yesterday, right? So you formally differentiate the power series. So this is the left-hand side of this equation. Now you plug the power series into the right-hand side of the equation, you get something like this, right? So the negative x, it's just minus the power series, but the epsilon x squared is in terms of the Cauchy product. And now you can take out the sum from n equals 0 to infinity, take the t out, combine these into a single series. And now you're ready to match like powers. Okay? And you get this recursion relation for the n plus 1th coefficient in terms of all lower order coefficients. Right? And it's a recursion relation, but it's a deep. It goes all the way back to the 0th coefficient. The current coefficient depends on all the earlier coefficients. Okay. Right, so if you can just solve for the n plus 1th, or sometimes we reindex, you like to write things just in terms of the nth coefficient is this formula of the lower coefficients. Okay. So, you know, that's something you can easily do on a computer, right? So let's say we want to compute to order n. So my 0th coefficient is just the initial condition. And then for n equals 1 to the order that you want to compute, your nth coefficient is given by that formula. And then you just return those coefficients. That's a Taylor integrator, right? So this gives you the Taylor expansion of the solution of the initial value problem to any order you wish. Okay. Okay, that's expanding just in time. You might want also to expand in space, right? You might want to expand the flow near the point x0 in both space and time, and it goes exactly the same way. You just try to write the flow as a sum power series in x and t. Okay, we'll take the initial condition x0. So now I have a m's and n's. When n is equal to 0, I need to say what to do. So when n is equal to 0 and m is 0, that's my initial condition. Okay, when m is 1, I give myself sort of a rescaling parameter here to play with. That's s, which is arbitrary, and then the others are just 0. Okay? So this is taking, you're going to take x's between -1 and 1 and map them into the interval x0 minus x, x0 plus s. Okay. So you do the same thing now, right? You just, you plug the power series into this equation. On the left, you're only taking a derivative with respect to t, okay? On the right, you just plug those power series into the differential equation. Now they're power series of 2 variables, so you're multiplying multivariable power series, but with it's just a Cauchy product again. So you match like powers and you get something very similar, right? Okay, so now you could just write a loop in a computer that computed as many coefficients in space and time as you'd like to expand the flow, right? Okay. If you had 2 spatial variables, 3 spatial variables, however many spatial variables, you could do exactly the same thing, right? Just develop power series of the flow. You just have multivariable power series, as many plus 1 as the dimension of your phase space. Okay, but between doing a Taylor integrator for an initial condition and doing a Taylor integrator for a whole box in phase space, there's a lot of room left in there. So something you might also try to do is integrate just some submanifold in your phase space. This is kind of a compromise, right? So the easiest thing to do would be to take an arc of initial conditions. So let's say that the vector field is never tangent to this arc. Then this arc, every point on the arc is going to move. So this is not at any point, this is not a solution curve. This is just what people call a material line. And you're going to try to flow this material line under the vector field. Okay, so like this, right? So you're looking for now a function gamma of s and t. It's going to satisfy this equation, and it's going to give you the Taylor integrator, or it's going to give you a Taylor expansion for the flow of this arc gamma. Okay, that's another thing you could do. So let me show you how that would go in the Lorentz equations. So these are the Lorentz equations. Let's say we pick a material line. So you pick any gamma you want, a curve in R3, analytic. We'd like to propagate that curve. Okay, so you want it to be, the vector field to be never tangent to the curve so that the curve actually moves. So we'll look for a power series for this thing, right? And then it's just like before. Okay, so you just take this formal series, you plug it into the differential equation. F of the power series is this, right? You have the coefficients A, B, and C. Those are the X, Y, and Z power series, or the components X, Y, and Z. Okay, so for Y you have the B's, for X's you have the A's. A times C, that's because of X and Z. A times B, that's the X and Y nonlinearity. Okay, you match like powers, and you can solve for the coefficients, okay? And this is actually kind of like a discrete dynamical system on infinite sequences, right? You start with an infinite sequence, the Taylor coefficients for your gamma. You apply this once, you get the first order coefficients, twice the second order coefficients, and so on. And you can compute as many coefficients as you like for the Taylor expansion of the flow of this curve. Okay? So here's an example of this in Lorentz. What we did here is we took kind of the worst curve of initial conditions that we could think of. We took the i's of the Lorentz system, which are equilibria, and the straight line between them. Okay? That straight line is going to get pulled all over the place by the Lorentz flow. Right? So here's a time step of 0.25. Now, what you see here is kind of the first. Okay, so we try to propagate this line as one power series as far as we can. At some point, those coefficients start to blow up, and then we stop and subdivide the curve into 4 subcurves. Then we further propagate those subcurves. Okay? So each one of these little squares is a patch in phase space parameterized by some polynomial. Okay? And those, for each one of those charts, we're taking 39 modes in space and 24 modes in time. That's a little bit arbitrary, but it's just giving good results in this problem. So that's 0.25 time steps. If you do this longer, then this is a disk, right? It starts at that line, and you're advecting that line forward, but it's getting smeared out across the Lorentz attractor. Right, so this is for one time unit, flowing that line, 900 and, almost 1,000 charts, describing how that material line propagates in forward time. And for each of these little patches, we have a power series representation. So a little power series describes this power series, power series, power series, power series, right? Okay. So this is Taylor integrators for material lines. Now, where do I want to use this? Remember, I started the talk talking about connecting orbits for stable and unstable manifolds. So what I'd like to do is advect the boundaries of some stable and unstable manifolds. Well, first I need the stable and unstable manifolds. So this is what I'll talk about now. Okay? So let's say we have an equilibrium point for some vector field. It'll always be analytic today. Let's say that the derivative is actually diagonalizable with m stable eigenvalues. Okay? So I want to find a chart map, a parameterization, so a map from the m-dimensional disk into my phase space, taking the origin of the m-dimensional ball to the equilibrium, and so that the image of the ball is in, say, the stable manifold of P. Okay, and the unstable is exactly the same, but I'll just to not say stable and unstable all the time, I'll just say stable. Okay. Okay. Yeah, we want that P parameterized as a local stable manifold. So I'm going to use to do this the parameterization method from the work of Cabré-Fontique and De la Ave. So this is the idea. I want to compute such a chart map. Right? I would like to find an equation that the chart map solves. That's the idea of the parameterization method. If I can reformulate this search in terms of finding a zero of some equation, then I have more tools. Okay? So here's the setup, right? You have the vector field on Rn, this equilibrium, m stable eigenvalues. Down here is that m-dimensional disk. So I'm looking for P that embeds this disk in Rn, right? Now, this is a choice. The rest of this, you start making choices, okay? So the thing you might decide to do is take the vector field generated by those eigenvalues and impose that vector field down in the disk. So in your parameter space, you now have fixed the dynamics, Okay, so it's just this linear differential equation. So lambda here is just the matrix of the m stable eigenvalues, the diagonal matrix. Okay? Okay, well, P is going to embed the disk, but the derivative of P is actually a device that takes vector fields down in that parameter disk and lifts those vector fields to the image of P. Okay? So this push forward of the vector field lambda defines some vector field over here on the image of P in phase space. What you'd like is that the vector fields match. Okay? So here's the image of P. You can define two vector fields on that image. You could take F and restrict it to P. That's a vector field. It attaches vectors to this image, to this disk. Or you could look at the push forward of lambda. That's another vector field, and I want them to be the same. So this is an equation we'll try to solve. Okay? Okay, so just a little more notation, right? My sigma is really a vector of parameters. Lambda is this diagonal matrix of eigenvalues. Sigma times lambda is like this. Okay? P is actually n maps from Rm into R. And this operator, the derivative of P, this is derivative with respect to sigma 1 of P and so on. Okay? So let's write that left-hand side of the invariance. The push forward of lambda is just like this, right? Lambda 1 sigma 1 partial of P with respect to sigma 1. And you do this for each sigma, except this should be a sigma m. Okay? Maybe it's fixed here. Yes. So this is a system of n scalar partial differential equations, nonlinear, all coupled. Okay? But it's not a boundary value problem. It's you have initial data, right? You want that the P takes 0 to the equilibrium point, and that the kth partial at 0 is equal to the kth eigenvector. So this is not so hard to solve, again, with power series methods. But first, let me try to, well, okay. Let me go back just real quick to this slide. Something I wanted to say. So why do we want that these vector fields match? If these vector fields match, then they generate the same dynamics. Okay? And the dynamics over here, I know. So if the push forward of this vector field matches the dynamics given by F, then the dynamics on this disk should be conjugate to the dynamics over here. So let me say that again with the picture, right? We have P taking the disk up into the phase space. We can run the dynamics down in the parameter space. You explicitly know that they're given by e to the lambda t sigma. So you pick any point in sigma, you know how to compute the trajectory downstairs for that sigma. Or you could pick a sigma and push it up here and flow, right? Okay, so if you take this orbit and map it up, you get a curve, certainly up here on this manifold. You want that this curve is a solution curve of your differential equation. So you want that these dynamics commute, right? So that picking a point down here on the disk and doing the linear dynamics, it's the same as first going up to the phase space and then doing the flow generated by the vector field. Okay? So, yes?
In that case, when you are looking for invariant manifold, you need an invariant equation that represents that you always stay in the invariant manifold in the dynamics of the set that you are.
So you pick the shape of your disk so that the linear dynamics always keeps orbit. So down in the parameter space, everything always goes in. Okay? So I'm not sure what you're asking.
I am not sure if the invariant equation is in the previous slide.
Yeah, okay, so let me prove a lemma, right? Something has to be said.
I'm sorry,
Okay?
do you know that such a P always exists?
No.
No.
Okay? You don't. But if it did exist, I want to say that would be good. Right? If there was one, then that would be good. That's where I'm starting now, right? Okay, so I don't know if I'm about to answer your question, but let's see.
Well, the question is, how do you know that the flow, the point that you start, stay all the time in the manifold? That you have to give a condition to.
So, dp is the tangent space of the manifold. So you're pushing forward the lambda to the tangent space of this manifold. So if f is going to be equal to that, then f is always tangent to the image of p. That's what this invariance equation says. Right? Okay. But let me try to prove it, right? Because you should. So suppose you have a solution to this equation with these initial conditions, okay? Then you have this flow conjugacy, all right? So that's a good reason to solve this equation, okay? So how do you prove that? Pick any point in the m-dimensional ball. E to the lambda t stays in the ball for all time, okay? So now I have a curve down in the m-dimensional ball. So let me lift that curve up into the phase space. So I'm going to define a new curve in Rn. It's just the image of this curve down in the parameter space. Okay, now let's differentiate that gamma. What I want to show you is that this gamma solves the differential equation. Okay, so first, take the derivative of gamma. By the chain rule, what is that? You'll have a derivative of p at e to the lambda t sigma. Then you have the derivative of the inside, which is this, right? Lambda's diagonal, so these things commute. So I'm going to introduce, just for a moment, this variable tilde sigma. It's e to the lambda t of sigma, okay? And I do that just to see that this, which looks kind of complicated, simplifies, okay, when I just make this little change of variables. So this is now the derivative of p at sigma times lambda sigma. Well, now I use this invariance equation. So that's f of p of sigma, okay? And I can do that because this is still in the ball. Okay, but now let's remove that tilde coordinate. This is really f of p of e to the lambda t sigma, but that's f of gamma t, okay? So gamma is a solution curve for this differential equation. And it's the solution curve with initial condition p of sigma, right? So now by uniqueness, this gamma t, it's actually the flow of this point, okay? But this is what I was claiming was true, right? That the flow of p of sigma for time t is p of e to the lambda t sigma, okay? So if I solve this equation, I have this flow conjugacy. Let's just make sure that this flow conjugacy gives me a local stable manifold, okay? So the image of P is certainly a disk. That disk contains the equilibrium point. That disk is also tangent to the stable eigenspace because of the first order conditions you impose. Okay, right. So now let's take anybody in the disk, look at the image. I want to see what happens when I flow that point forward. Okay, well, because of the flow conjugacy, the flow of P of sigma for time t, this is just P of e to the lambda t sigma. As long as P is continuous, the limit comes inside, and this limit I know because these are stable eigenvalues. So this is P of 0, which is the equilibrium point. So any point on the image of P limits to the equilibrium. That's a local, well, that's certainly a subset of the local stable manifold, but since the, image of P is an m-dimensional disk containing the equilibrium and tangent to the eigenspace at the equilibrium, it really is a full local stable manifold. Right? Okay. So that's kind of the idea behind the parametrization method. So if it's a good idea to solve that invariance equation, let's see how you actually solve it. Okay? So here's, again, the Lorentz system. Let's consider just a one-dimensional stable or unstable manifold. So one, let's say, stable eigenvalue. Okay, so then the invariance equation reduces to this ordinary differential equation. I can look for a power series solution for this equation. I know the 0th and first order conditions. So if I take the derivative with respect to sigma, that lowers the order here, right? I'll get the n, then I bring in the lambda, so I get an n lambda, sigma n minus 1, but then I bring inside the sigma goes back up to the power of n. Okay, so this is the formal series version of this operation. On the other hand, if I take f composed with p, that's just power series operations like before, so that can all be written in terms of the power series and convolutions. Cauchy products. So you set those equal to each other, and it's a little different from what you had with the Taylor integrator. With the Taylor integrator, I had ANs as a function of lower order things. Here I have ANs on this side and things of order n on this side. So I need to isolate, I need to extract anything of order n over here. Some of them I see very clearly, but we should look inside the Cauchy product. So there's the Cauchy product, right? How do I get something of order n? Well, if k was 0, I'd have an times c0. And if k was n, I'd have a0 times cn. And those are all the terms of order n. Right? So I can write it like this. Now, I'm going to do this operation so many times that I'd like to give this thing a name. You know, the Cauchy product with nth order terms extracted. I'll call this a Cauchy hat product or something, okay? Okay, and it's the same thing for A times B. So now, I go back to this F composed with P, and I just rewrite it with the nth order terms taken out of these Cauchy products. Now I'll put everything of order n by itself, and lower order things by themselves. What you notice is that this is linear in AN, BN, and CN. It's this matrix. A0, B0, and C0, those are the components of your equilibrium solution. So what you notice about this matrix is it's actually the derivative of your vector field. Again, I'm doing just Lorentz here, right? The derivative of my vector field evaluated at my equilibrium, plus lower order things. Okay, so if I go back to having matched like powers, this can be rewritten like this. Now I'll put things involving AN on one side and lower order things on another, and you get these homological equations, where Pn is the AN, BN, CN, and Rn is a right-hand side depending on things of lower order. So you can recursively, or you might hope to recursively solve these equations. Now, to your question, at least in this case, when can I solve this equation? I can solve it as long as this matrix is invertible. I'm only interested in n greater than or equal to 2. I assumed I had only one stable eigenvalue. So n times that stable eigenvalue will never be a stable eigenvalue again. Will never be an unstable eigenvalue. So this is always invertible, this matrix, at least in this case of one eigenvalue. So this series is formally well defined. Okay? So here's an algorithm for computing the thing to any order you want. First you find the equilibrium, the eigenvalue, the eigenvector. Right? Now for n equals 2, to whatever order you wish, you first compute that right-hand side R in terms of things you already know. You solve this linear differential equation, which is not this linear equation, linear system of equations, where this matrix is for sure invertible. and then you keep the result. When you're done, you return all of those solutions. Those are your coefficients for the manifold, for the parameterization. All right? So here's some parameterizations to order 50 for the 1D manifolds at the I's and Lorentz. Okay. Well, you can do the same thing for higher dimensional manifolds. Okay, so my invariance equation becomes now a PDE. It's really a PDE. And I'll look for a 2-variable power series solving. Then everything kind of goes like no different from before. My first order conditions, I need to, my 0th coefficient will be the equilibrium. My first order coefficients, the eigenvectors. Okay, so on the level of formal series, this operation, it's kind of like what we had before, but 2 of them, okay? So, here I have lambda 1, but I'm taking derivative with respect to sigma 1. That brings down an m. And this raises the order back up. Okay, I have derivative with respect to sigma 2. It brings down an n, but this raises things back up. So I get this. Okay, and the f composed with p, this is the same. Okay, this is just computing products of polynomials. Products of power series. So you get the same homological equations, more or less, except now the hat product should be the Cauchy product. You have these as your mn order terms, your terms of order mn. Okay? Now, let's see. If these were real and distinct, then you could have a resonance here. But there's only a finite number of chances for that, because eventually, m and n are big enough that m times lambda 1 plus n times lambda 2 is bigger than either lambda 1 or lambda 2. Okay? So for high enough m and n, this can't be in the spectrum. But there are a finite number of cases you always have to check to see if you have any resonances that you can invert this matrix. Or numerically, you just start trying to compute it, and if the computer ever complains that you had an ill-conditioned matrix, then you suspect you had a resonance and you go back and you look harder. Yeah?
You can put the resonance inside
You can get around a resonance. Okay, so I'm keeping it a little simple. I'm only going to use as much as I need for today and tomorrow. If you have a resonance, yeah, you need to conjugate to different dynamics. I'm conjugating to purely linear. If I had a resonance, I would conjugate to linear plus a polynomial that exactly killed that resonance. Yeah, but that's more than I sort of need today. The other thing to say is that if these are complex conjugates, which is the case I care about for a saddle focus, then this can never happen. So again, if I have just 2-dimensional manifolds associated with complex conjugate eigenvalues, there's no possible resonance, and the parameterization is formally well-defined to all orders. So the algorithm is, now you compute the equilibrium, now you have 2 eigenvalues and eigenvectors to compute, and now you have a double loop, right? Well, you should now check, maybe, whether things are resonant. If they're resonant, you stop. If they're not resonant, you keep going. Okay, and from order 2 to order n, you solve these equations. And you return all of these power series coefficients. And this is more like a matrix, right? You have P00, P01, P02, so on, P10, P20, P11, right? It's a data structure like this. Okay, so here's some examples in Lorentz. The blue manifolds are the unstable manifolds of the I's. These are computed to pretty high order because the dynamics at the I's are not resonant, but they're very slow. So I need to compute to high order to see anything. But the manifold at the origin, I have distinct eigenvalues. This is a parameterization of the stable manifold at the origin. Okay, to order 50. Okay. Now, I want to combine the stuff that I've been talking about.
So what if the map in sigma is not the map, but the vector field in sigma is not linear? You have a sigma squared or something different vector field instead.
In the parameter space?
Yes, the parameter space.
Like if you had a resonance?
Well, no. I'm talking about going back to the, let's say you're trying to parameterize a manifold that's not, you don't have linear dynamics in the manifold, but you have something like quadratic dynamics or cubic.
So, well, things are different, right?
So I'm thinking of something like a parabolic manifold.
Yeah, center manifolds. This is harder.
Yeah, center manifolds.
Okay, this could be maybe 4 or 5 other talks, I guess.
Okay.
But things can be done, of course, and if you can compute F composed with P, yes, then you can kind of do what you're asking. But the invariance equation is different. You try to write things as a graph. I don't know, so I'm trying to understand what you're asking me, really. I'm not trying to say that one can parameterize everything you could ever with this. What I'm trying to say is if I have diagonalizable and I do just a stable or just an unstable, that things are kind of like this. So I don't know, I feel like I've misunderstood your question.
No, I was just asking about really what you said about center manifolds.
For center manifolds, you have to do other things,
yeah,
but not so different.
Yeah.
In the second manifold, it's not unique, the solution, isn't it?
The Taylor coefficients are unique.
That you have to choose the regularity.
Yeah. It's way harder.
But you have to set the regularity that you want to.
Yes, and you kind of pick, you try to write it as a graph, and then you pick you make more choices even. Yeah. Okay, so let's say now I have this parameterized local manifold. I want to combine this with the Taylor integrator for advecting arcs. Why? The boundary of this manifold is, say, a circle, which I can cut up into a number of arcs, and then I can try to propagate those arcs. Right? So I can grow this manifold by combining the things I've been talking about all afternoon. If I flow the arc a little bit and the computation gets unwieldy, I can subdivide the arcs just like we were doing for the line I showed you earlier. So here's advecting the stable manifold I showed you a little earlier for one time unit in backward time. This is about 5,000 polynomial charts, each order 24 in time, 39 in space, which is again a little bit arbitrary. Okay, but so you can grow these things much, you can get far away from the equilibrium. So the local parameterization, it's some disk near the equilibrium. It's not always that exciting, but you start to grow this thing, and of course, it can get very complicated. Okay, but the point of this picture is that the surface that you're seeing, it's a manifold, piecewise parameterized by 4,600 different polynomial charts, right? Okay, and now you can go in and look at what you did, and you can look for things like connecting orbits, right? So this is a manifold near the eye, and this is like a little piece of the big picture I just showed you, and it looks a lot like these intersect transversely, so there's some heteroclinic connection between those manifolds.
So is there a systematic way to decide the orders of the polynomials?
There's a lot of heuristics that we use for that, and we don't have a ton of theorems. So there's a lot more work to be done on that, I think. Now we play around until what we do is we fix always an order like this, and then we subdivide in time or space as needed to make this work. You see what I mean? But one could also do adaptive order in space and time, and there's a lot more to be done there. Yeah.
Extending from the center to this point, there might be some error when you start.
Of course, there's error. Yeah. So this is what I'll talk about tomorrow when I talk about how to validate these computations. But this that I showed you, this is actually validated. So everything in this picture, I think the worst error is 10 to the minus 4, and that's a theorem. Yeah? So this is a computer-assisted proof for each one of those 4,600 charts that the error is less than something. But this is what I maybe talk about tomorrow.
So can you explain that picture once again?
This.
No, the following.
This.
Yeah.
This is one little piece of the big picture I just showed you near the 2D unstable manifold of the I. So stable manifold of the origin, unstable manifold of the I. They intersect transversely, so there's some orbit, which people have seen, of course, but there's some orbit that comes out of here and goes right into the origin. Right? Okay.
Sorry, one last question.
Yeah?
So, for example, you select like an error or a tolerance, and then fix some other things, so the orders in your approximation to make your tolerance work.
Yes.
Same to the -4.
Yes. Well, what we try to do is we try to lose less than a certain amount with each step. That's what we really try to do. And then when the total thing has gone above 10 to the -4, we say, okay, we're done. You see what I mean? But at each step, we say we don't want to lose more than 200 multiples of machine epsilon or something like this. And then things adapt to that, right? Okay, great, good. Okay, so all that is very plausible for a quadratic vector field like Lorentz. Interesting problems are not always quadratic. So what do you do when you have non-polynomial problems like the restricted four-body problem I said I want to talk about? So there's an idea that some people refer to as automatic differentiation that I'll try to describe, okay? So this will let me deal with nonlinearities that are not polynomial but that involve elementary functions.
What do you mean by elementary?
You know, okay, what do I mean? The functions I teach my freshman calculus students. These functions, actually they need to be functions that themselves solve polynomial differential equations. That's really what I mean by elementary functions. Yeah? But these and Bessel functions and all of the mathematical physics, elliptic integrals and things like this, right? Yeah. Okay. So that's part of the idea of this automatic differentiation is that nonlinearities like these solve polynomial differential equations. And the other thing is that, of course, differentiation turns function composition into multiplication. And combining these two things, you can turn your problem into a polynomial problem. So here's an example. Again, a simple example with a non-polynomial nonlinearity. So I want to write this as a polynomial problem, but maybe a system of equations instead of one equation. Okay, so the trick is to let y equal e to the negative x, and then I differentiate y. I know x prime, and I know that e to the negative x is supposed to be y, so here I have a polynomial, right? So this equation for y I append to the other equation. So I have this system of equations with these initial conditions. Okay, so I'll solve this instead of the given problem. And this is a polynomial problem. In fact, basically, this is as complicated as Cauchy products now. So to solve this, a Taylor integrator for this is like this, right? I just assume power series solutions x and y. These are the formal derivatives. You plug things in on this side of the equations, you get Cauchy products like this, right? So this is a recursion scheme that will now let you generate as many coefficients as you want for A and B. The price you pay is that you have to store the coefficients B. So you're storing twice as much as you had to before, okay? But if you're going to compute a few thousand coefficients, then a few thousand more, this is not a memory problem for even a computer like this, right? But that is the price that's important to say.
Well, I mean, memory is cheap, right? But you have to perform more operations?
Okay, twice, of course, you have to perform more operations. Mm-hmm. Yeah. So you're right. You pay in memory, you pay in time. Yeah. This is not so bad, but this is worse. This is cubic instead of, but okay, but it's better than the e to the negative x, which if you tried to expand as a Taylor series or something, Chebyshev series or something, you'd probably do worse than this, right? Okay, so this is a nice trick. when you're doing a proof, you'd like to say, really, why do you think this is working? And I like this explanation. So you have a non-polynomial vector field. Let's say this f has m non-polynomial terms. Okay? So you're going to look for a function r, which, okay, so f might not be defined on all of Rn, just on an open subset. So you look for an r from that set, u, into Rn, but plus m variables, okay? That can be written basically as a graph. Okay, so R should be just x in its first n components, and then h of x in the next n. And then I want to find a polynomial vector field G so that this conjugacy holds. Okay? And this looks a lot like the parameterization method for invariant manifolds a minute ago. It's a infinitesimal conjugacy relation. Right? So the important thing here is that G should be polynomial. Okay? If you can do this, then you have orbits of G with initial conditions in the image of R project down to orbits of F. Okay? Which F was your non-polynomial problem. So to see that, what are we going to do? Well, suppose you have a solution of the differential equation for G. This is the polynomial problem with initial conditions on R. Okay? Then I can take just the first n components of R of x, which is just x0, and I can look at the solution of the non-polynomial problem. Okay? Okay. So now you imagine taking that curve from down in your non-polynomial problem and lifting it up into Rm plus m by this. Okay? Well, this is now a curve in that n plus m dimensional phase space. You differentiate, okay, and you see that it solves the differential equation for G. Right? So this tells you a number of things. It tells you that gamma t, right, the solution in the bigger space, is R of the solution downstairs. It tells you that the image of R is invariant, because if you start on it, you stay on it. And it tells you you can recover the dynamics from F by looking at the dynamics for G and then projecting into the first n coordinates. Okay? Okay, so, you know, I did something a little bit formal to get from this equation to the polynomial equation, but here I take my R of x to be the x and then the e to the negative x. That's the initial condition for my second component. My G is the polynomial vector field we derived in the earlier slides. You can check that this relationship holds. Okay? That drf is G of R of x. And so the dynamics of this system, the dynamics of this with initial conditions here, is the same as the dynamics of this. Okay? Okay. So what about for the restricted four-body problem? So this was the vector field for the restricted four-body problem. You can go through the same kind of stuff, right? So there's your F. It's non-polynomial. It's defined on an open subset of R4. I'm going to introduce these variables that are going to get rid of the 1 over R terms, which are kind of really the non-polynomial part. Okay? Let's look at one of those, the Z1. You differentiate it. Okay? You get, this to the minus 2/3 power times the derivative of the inside, right? Times the x prime, y prime. But x prime is one of my variables for the vector field. That's v, and y prime is w. And then here, I can rewrite this as a minus 1 over the square root, then to the 3rd power. So this is z1. Right, so you have a a polynomial expression again. And for all three of those, R1, R2, R3, it goes the same way. So now you can just check that for this f, you look at this polynomial vector field, G, and what are you going to do? I'm going to now work with this polynomial vector field instead of this, non-polynomial vector field, right? And the R is here, and you can check that these satisfy the conjugacy relation from this theorem. Okay? So to work with the restricted four-body problem, we'll work with this polynomial vector field instead of this when we're doing the Taylor integrator, when we're doing the parameterization method. Okay? Because then everything just becomes multiplication of power series. Right? Was there a question?
No. It's just that what you are using is that every one of the elementary functions are given by some differential equation.
Exactly.
Okay.
Yeah.
So you can treat that this way, even very complicated functions, because most of them are...
If I could write it in a Calculus 1 class, then we could do this, right?
But what if it's a higher order differential equation? Let's say, you chose, first you chose the exponential, right? Which satisfies the first order differential equation.
Then you append, okay, then I write it as a system of first order and I append the system of first order. So for sine and cosine, I have to do both.
You have to do both.
Yeah, if I have a sine nonlinearity, I have to also do the cosine and,
What I'm saying is that for the exponential, you have to append one equation. If you do sine or cosine.
Yeah. So maybe my count, I said m should maybe be more than I said, but you get, it's the same idea. However many times I do this, I append an equation, and that tells you where all these things map.
No, what I'm thinking is that if I can think of a function that's defined by a differential equation of order 47, then you will...
Yeah, you'd have to append a lot of equations. 47 equations. Yeah.
But in that case, the second equation, the differential equation, I say that it's important to write like a polynomial differential equation. But I don't know if for any vector field that I have, it is possible to obtain the second equation like a polynomial equation.
So,
because in that case, you have the trick that you...
If I have something like sine composed with e composed with the square root of x, right? Then first I do the square root of x, then I do sine, then I do e. You see what I mean? I'm going to have to do this many times. So I don't try to say that sine of e of square root solves one equation unless I can figure out a clever one. I do the square root first, and the e next, and the sine next. I have to decompose it into pieces where I can do this, one at a time.
Because, well, I am not sure, right? But looks like you need that the nonlinearity in your vector field. You need that this nonlinearity part depends that there exists a rational, the polynomial differential equation whose response is this function.
That's what I will define to be an elementary function, is what you just said. So a function is elementary if it satisfies what you just said. And for such functions, I can do this. And for other functions, I have to do something else.
Because in general, you expand.
Again, this is for like things that I could just write, that I would write down, right? I mean, I'm not saying this wouldn't, I mean, in some like generic sense, this works on a, never, right? But for any vector field that a physicist or an engineer would bring into my office, this is going to work, right? Okay. Thank you. Okay. So now let's say a Taylor integrator for moving analytic arcs in the circular restricted four-body problem. I try to write it like these. I need these coefficients, gamma, n, and m. Okay, where I want to propagate some arc. The m and 0 coefficients are the coefficients of the arc. And you can work out, you know, the next, so coefficients of order n plus 1 depend on the lower order guys in this way. Okay, and this is, it's complicated, but it's all convolutions. It's all, sorry, Cauchy products. It's just multiplications of power series. But this is the main piece of a Taylor integrator for the circular restricted four-body problem, a Taylor integrator for arcs. For the parametrization method, okay, for the parametrization method, if you have an equilibrium with, say, two stable eigenvalues, then the homological equations are these, where R can be written down in terms of these hat products. So these are Cauchy convolutions with the highest order terms removed. Okay? And so these are the homological equations. You solve these one at a time to compute the manifolds. So let's see. The equilibria in the four-body problem look like this, right? So there's M1, M2, M3. These are the singularities where the masses are sitting. This is kind of a cartoon of the dynamics. So like I said yesterday, there's either 8, 9, or 10 equilibria. This is a picture when there are 10. Okay, so 4 inner libration points and 6 outer. Let's see, so here's the inner libration point. If you start close to the equal mass case, is saddle focus, right? So here it's local stable and unstable manifolds with the hill regions parameterized to what? Order 45. Okay, so if these are 3 stars, then these are pretty big manifolds, right? Or if this is the sun, Jupiter, and a Trojan asteroid, these manifolds are pretty big, right? For different mass values, right? Different parameterizations of those manifolds. Okay, here's the situation at the, so now I'm going to talk about the case of equal masses. M1 equals M2 equals M3 equals 1/3. So now you have the 10 libration points, 1, 2, 3, 4 are saddle focus, and the remaining are saddle center. And of course you have the Lyapunov families for these other guys, right? But you still have some saddle focus stuff going on too. So the saddle focus stuff is the stuff that Shane studied in his thesis. So this has a rotation by 3 symmetry. So we'll look at this manifold and this manifold. We'll focus on these, what L0 and what we call L5. Okay? So here's at L0. We took this. These are the parameterized local manifolds in the middle. We mesh the boundary into 30 arcs, and then we can propagate those arcs with this Taylor integrator. So there's for time 0.25, 0.75, time 1, 1.25, and so on. So this is by time plus or minus, so +4 for the unstable manifold, -4 for the stable manifold. So these are each chart, order 20 in space, 40 in time, almost 10,000 stable charts, unstable charts. This took an hour to compute. Now, you have a problem when you get too close to the primaries. Right now, the way we're solving that problem is if our velocity exceeds a certain threshold, we throw a chart away. Okay? It's not the best way to do this, but it still gives us a lot, right? At L5, you can do the same thing. Okay, so this is again, these local manifolds at L5. That's 0.5 time units, and so on. So plus or minus 0.4, and you have about 5,000 charts for each atlas. This also took about an hour. Okay, so these are cool pictures, I think, but you'd like to now go inside and mine this data. So you have thousands and thousands of charts, you know, representing this manifold. So what we were interested in are homoclinic intersections. So you want to go in and look for patches like this, right? So that in the 3D energy level, a 2D guy and a 2D guy that intersect transversely. Okay, because That's the hypotheses of those theorems from the beginning of the talk. So here's a picture of one at L5. So you go and you find these charts way out here. They seem to intersect. We check that numerically, of course. And then we keep track of the parents of each chart, so we can follow that back to the local manifold. And that gives you kind of an approximation of the connecting orbit that you could do a lot of things with. If you have validated bounds on these charts, you could just try to prove that you really do have an intersection. You could also use this as the initial data for a boundary value solver and get much more accurate representations of these orbits by solving boundary value problems. So this is your kind of initial data. So if you take the atlases that I showed you a minute ago, the one at L0, the one at L5, and you mine these for homoclinic connections, we find 42 at L0 and 23 at L5. Each of these 42 has a rotational counterpart. Okay, so each orbit we find here, if you rotate by a third, you get a different homoclinic orbit. So really there's, 126 connecting orbits that come out of that data. And here you have 23. If you rotate these by a third, you get connecting orbits at this libration point, and rotate it again, you get ones here. So these have symmetric counterparts. Also, okay, let me see how much time I have.
10 minutes.
Okay, great, so I'm almost done. So it's fun to kind of look at these a little harder. So at L0, we look at the two shortest connections we find, and they look like this, right? So one seems to be related to the Lyapunov family at the libration point that's here, L2. Quite possibly the Lyapunov family actually accumulate to this orbit with the blue sky catastrophe, but we haven't explored that yet, right? But that's what it looks like here. And this seems to be related to some periodic orbits around the primaries, right? And if you rotate these, like I said, you have actually 6 orbits that look like this. And then all the other connections that we find are kind of built out of these, right? So here's one that loops twice around that same loop, starts to loop around one Lyapunov family and comes back around another, sort of visits all 3 Lyapunov families and so on. Or we have things that maybe go around multiple bodies, things like this. This looks like I'm just showing you the same orbit from the first slide, but if you zoom in, you see that, it actually almost comes back and then goes out for a second excursion. So it really has winding 2 around this primary. Right? Okay, so we find a bunch of, this is kind of all of those orbits from that search. And then at L5, you have sort of 6. A bigger alphabet, right? So orbits like this that make an excursion, sort of a funny double excursion, and things that go through the middle without winding around any of the bodies, and things that go around the outside. And then everything else we find is somehow built out of those. Even these much longer guys. So here's one that has winding around all 3 primaries. Okay, so yeah, as I said, you can switch to a boundary value formulation for these connecting orbits. And once you've moved to that setting, it's natural to do continuation. So you can move the mass parameters and try to follow these things. And this is some continuation almost, okay. So at some point, L0 stops being a saddle focus. And here this is a continuation almost to that point for both those shortest families. And same thing at L5. This is continuation almost until L5 is going to lose saddle focus stability. Okay. Okay, so this has generated a ton of numerical conjectures, right? We conjecture that each one of these pictures corresponds to an actual transverse connecting orbit in this problem. And we'd like to prove that there are actually transverse connecting orbits there, because then for each one of these, the theorems, these classic theorems from Hamiltonian systems kick in and give us blue sky catastrophes and symbolic dynamics nearby and so on. Okay? So, we need to validate the parameterizations, we need to validate the Taylor integrators. And in both cases, we had nonlinear recurrence relations like this. Okay, so tomorrow what I'll finish up with talking about a little bit, or I'll actually I'll show you the whole thing, but for a simple problem, how when you have nonlinear recurrence relations like this, you can think of this as a fixed point problem. You can solve the recurrence relation exactly to high order, and then you can check that on the tail, the map that's left is a contraction. You can do very simple computer-assisted proofs that give you validated bounds for your Taylor integrator, for your parameterizations. There may be the simplest infinite dimensional computer-assisted proofs I've ever seen, just exploiting that you have explicit recursion and the contraction mapping theorem. So I'll go over that tomorrow. Okay? And that's all I have to say today. Thank you.
Hay preguntas para Jason.
What change if I use Chebyshev polynomials?
So, yeah, for an initial value problem, Chebyshev is much better, actually. You could take much longer steps. I don't know if John Philippe will talk about this tomorrow or not, but we also use Chebyshev when we are doing boundary value problems. They're much better for boundary value problems. For spatial problems, you have to do like Chebyshev, and this is harder. And even in the numerical computing community, this is something kind of new. So there are some nice numerical methods, right, coming out now doing Chebyshev, and so forth. But a lot of those methods aren't validated yet. And for some problems, it's actually very hard. And John Philippe has done a lot of work trying to combine a Chebyshev dimension with a Fourier dimension and things like this, and has some results, but they had to work very hard. Yeah. So I think a nice thing to do would be to do Chebyshev in space, so there's no derivatives, and Taylor in time. This is the first thing I might try. And then you'd get recursion, order by order, but on Chebyshev coefficients. So it would be a lot like this, and that would let you take bigger arcs in space. Maybe it wouldn't let you integrate any longer, but you'd have to cut less, so this would be globally better, right? So what I talked about today could probably be improved using an idea like that. But certainly for boundary value problems, John, you will talk about periodic orbits.
I will mention Chebyshev, but I will not go into detail.
Okay. So we're happy to talk about it. We love Chebyshev. We use Chebyshev. Right now, Chebyshev is working great when you really just have one variable. Is that, do you think? And then starting to work in some other cases. Yeah. Yeah.
When you say one variable, you mean one per perturbation?
Like just in time. Or you're doing a 1D, 2-point boundary value problem. That's actually perfect for Chebyshev. Right? You're going from this point flowing over to here. Maybe an Rn, so you have lots of Chebyshev, but Chebyshev in one variable. Yeah. Yeah.
It's possible or convenient doing the method of the parameterization in homoclinic points. I mean, doing a parameterization for manifolds in fixed point, and next parameterization in homoclinic point.
Homoclinic.
In intersection between manifolds.
Yes, you could. Okay, so if you have the manifolds are intersecting, okay, you could try to do a Taylor expansion of that intersection using that some manifolds have intersected. What I think is nicer is to solve a boundary value problem with Chebyshev for that intersection. This is, I think, really the best thing to do if you want the most accurate representation of that intersection, of that connecting orbit.
And then we can choose another way for parameterization in the beginning.
If you had a center manifold and you parameterized that and you were doing some connection for a center manifold, you could do that also as a boundary value problem. The hard part would be computing the center manifold. Yeah. Yeah, okay.
Okay, if there are no other questions, we thank Jay again.
Thank you, guys.
We will soon with Jean-Philippe's talk at 5:30, so that's around 10 minutes.
Thanks for the questions.
If you have this kind of parameterization of the invariant manifold, this is the best way to determine the intersection of the stable and the stable manifold. Because